Welcome back. We left off on Tuesday. We were talking about texture mapping, and I think we now all can see, the main motivation for why it exists. And today we're just going to talk more about the mechanics, look at just a couple of demos of what kind of the bare minimum texture mapping example needs to look like, and that hopefully will influence some of the hardware design you'll be doing. And as I mentioned on Tuesday, I think you really want to start as simple as possible with your examples, get those working, and then you can start to debug more complex things. At a high level, the integration of texture mapping is kind of a merger of two different sort of pipelines that we already have here, right? So we have that top view here in this diagram is kind of the traditional rasterization-based pipeline here from geometry to frame buffer, but we know separately there's this other mechanism by just kind of copying raw blocks of data. You can think of that as a separate pixel processing pipeline where I want to clear a buffer or send some values to a buffer. And in some sense, texture mapping is kind of a merging of that pixel processing pipeline with our more traditional rasterization, our geometry pipeline that we have here. And again, going back to the whole point of doing texture mapping, right, is it's to have that visual detail in our scene that is going to wind up being in that image and not in the geometry itself, so that you can, in theory, have relatively simple geometry, but with a lot more detail in the actual texture, so that the complexity of the image doesn't really affect the complexity of what's going on in the traditional geometric pipeline here. So it's added post-rasterization, as we'll see here. It is primarily a task being done in our fragment processing. Now, as with everything that we talk about the OpenGL mechanics for doing it, there is like the illustrative example, there's a couple like demo applications, and then like everything else in OpenGL, there's a really large like kind of state space associated with it of lots of little parameters you can tweak. And I think for those of you who require this for your projects, pick just a sane set of either defaults or set of things that you want to be able to implement. There's nothing here, although it starts to get a little tricky, but there's ultimately nothing here that you could not do. There's nothing beyond our understanding, beyond your hardware design expertise at this point in the semester. It's just a matter of time and resources, in terms of what you would like to ultimately implement. And we'll start with talking about, the actual task of mapping these texture coordinates. It gets a little bit tricky in practice because while we already have the coordinate systems we're having to deal with regards to our object or our world coordinates and all the transformations that happen therein, we have our final window coordinates where things are going to appear after our viewport transformation. We also now have this whole additional coordinate system that we're having to try to manage here. In general, for texture mapping to make sense for your application, either A, you're starting with some rendering software, some modeling software, that's going to generate the texture coordinates for you, or B, you're going to have some mathematical model of how you're going to be applying those texture coordinates. So when I keep mentioning parametric coordinate systems, that's all I'm talking about here, that if you know your object is a sphere or is comprised of mathematical functions and can be defined mathematically, then you can generate your texture coordinates yourself in your application because you can just use that mathematical model for that particular object or composition of objects. We already saw that, I think, maybe when we were doing just the globe example or the sphere example. That was doable, and the normals for that were doable because there was basically the model of a sphere, and that dictates what the normal should be for those individual vertices inside that sphere. Same for texture mapping a sphere, the same parametric coordinates would apply there. You have a sphere, it's got spherical coordinates, you can define them, the wrapping of that texture to that sphere based on those parametric coordinates, the u and the v versus the x, y, and z associated with that sphere. But otherwise, it's not a really straightforward thing. Part of the problem is not just the coordinate system itself, part of it is like how do we actually, generate or, acquire our textures in the first place. It's kind of tempting, I think, at first blush to say, I am going to take some still images of something I would like to map in higher detail in my particular scene and map some subset of those photographs, those still images, onto my geometry. You can do that. You can make a Jones cube, as we talked about on Tuesday, and for that kind of thing, it does work. It's not like it's improper to do that. But if you're trying to model something that's the attempt to look more visually realistic via texture mapping, then acquiring real-world textures in that way doesn't tend to work especially well, because the real world has really complicated lighting going on, right? Really complicated combinations of reflecting and illumination, and we have a lighting model, and we can combine a lighting model with a texture mapping process, and your fragment shader can really just merge the two results of both those programs together, essentially. But the photograph we take has a kind of inherent lighting associated with it. This is a somewhat complicated example, but any photograph you take has got a lot of complicated lighting going on. When you then apply that to your geometry in an actual scene, your lighting model in that scene is not going to be an exact replication of what's happening in this particular real world example. So the lighting is going to look off, is the short of it, and it's never going to look exactly the way you want. That's one challenge in going from kind of real world imagery to rendering something that's meant to look photorealistic. And the second challenge, although it's one that we can overcome, is that when we take photographs, and as we talked about both the virtual camera system of doing rendering and how that kind of connects to choosing different lenses for your actual photographs, they tend to have perspective of some amount associated with it. And so your photograph will have a certain amount of perspective. Only if your scene has the exact same type of perspective associated with it will the perspective and the foreshortening of the pixels far enough away from your camera in the image correspond to the right amount of foreshortening you would want when you're doing the texture mapping of that image back to your scene. So for perhaps you could replicate something like this in your scene if it's static, if it's literally that scene with some very similar type of lighting recreated in such a mechanism. And we can, of course, right? If it's truly static, you can take this picture and apply it to a quad, and then you're done, right? Then it's just one rectangle and you've applied it. But if you wanted to do so in a 3D manner, which I think would be the intent of doing so here, you can't as easily just say, here's a triangle in my scene that's part of the floor, and I'm going to take this same exact region from our texture map that was from an image and expect to get something that's going to look especially correct. It's going to work in terms of generating some pixels back out, but you're not going to kind of recreate reality in such a way. There are some workarounds for this, but in general, that's still an issue. That texture mapping allows us to basically pretend we have higher resolution geometry than we really do, but it's not, a workaround for the entire challenge of doing photorealistic rendering. It can give us some more realistic effects, but we are limited in our capacity to acquire textures in a realistic manner and our capacity to map them in a manner that's appropriate for the geometry we have in a given scene. So how do we do this in practice? Well, we could just, just like with our normals, we could just type all the values in by hand, but that doesn't really work, doesn't really scale. In a sense, though, this task of texture mapping, and again, the OpenGL we're adding is just a couple lines. There's not a lot here in terms of OpenGL, but the mapping task of assigning those texture coordinates is somewhat, and I'm just going to say this in kind of a fuzzy sense, is somewhat analogous to what we already have to do. We are already, as part of our rendering pipeline, taking 3D geometry and ultimately converting it to a 2D screen here. Texture mapping, at least the conventional texture mapping, is doing something kind of analogous, which is we have a 2D texture and we're going to apply it to some 3D geometry. So the same kind of modeling approaches, they're not exactly the same, that's why I say it's a little fuzzy to think of it, but our mindset has to be kind of similar. We will have a globe object in our scene which is modeled as a sphere, which is made of composite, triangles. And we are going to have a two-dimensional texture, and I'm not actually showing the texture here. The texture would look like a flattened kind of map, but not like a Mercator projection of a map, but something kind of similar looking to that. And we have to determine what should the texture coordinates be, so it gives us the wrapping around that sphere. That's not so different than the task of modeling the sphere in the first place, where we have to think about, for the final 2D image we want to have, what do our three-dimensional triangles need to be in order to give us a spherical-like object. If we have something that can already be in a parametric coordinate system that we can just mathematically define, like spheres and like cylinders and things of that nature, we can do this kind of directly. When it is arbitrary geometry, this is Stanford Bunny model, you tend to get effects that look something like this. So you can map a texture to anything. You apply texture coordinates, you get a result back out. But if your object is not something that can be easily mathematically modeled, you either have to use specific software kind of dedicated to generating appropriate textures and texture maps, or you wind up with Zambrino cubes and bunnies with arbitrary wrapping paper applied to them there. For a cylinder, we can probably do it. If we know that our object that we wanted to map was a cylinder. So the Campbell soup can example here, even in this example, this is a computer-generated texture. If you took a photo of a label, that texture is still not going to look correct when mapped to a can in a particular scene. If our object was a cylinder in the scene, we could define parametric coordinates, right? It's like this sphere, except it's even simpler, right? So our x and our y would be that r cosine u, r sine u, like it was before for the sphere, but z would then be just the height. Z would be v or something like that. Or if our height is meant to be t, z would be v over t or v over h for the height of it. So we can mathematically, to define what our vertices need to be, use parametric coordinates. Just like for the sphere, instead of worrying about x and y and z originally, we just say we have the u and v corresponding to the rotation and then in this case the height of our cylinder. We can iterate through that to generate our vertices. We can then do the same exact thing for our texture coordinates as well. There's many possible solutions because there isn't one way to map a texture, but if we had a soup can texture and we had a cylindrical can we wanted to map it to, the straightforward solution that would look reasonably good is, okay, there's a lot of coordinate systems we're talking about here. U and V are for the rotation and for the height. X, Y, Z are for the vertices as we specify our geometry. And then we also need to generate S and T for our texture. You can think of this as the texture X coordinate and the texture Y coordinate, or the width and the height of our texture. So if U, we called it theta when we were doing it in our C code earlier in this topic, right? If U is our rotation around the cylinder, and we want to wrap this texture around the cylinder, what should our S coordinate correspond to in our texture map? Well, there is a radius, right? So, and it's not really shown here. So the answer is actually not the radius. So it's a good guess. I like it. So so the x and y are going to be radius times cosine u, radius times sine u. So we don't know what the radius is here. As we generate x and y, we're traversing the circumference of the circle to generate our points. For the texture map, the texture map is going to be somewhere in the range 0 to 1 for the valid texture coordinates, and it's going to map to that value of u that's presumably here. There's more than one way you can do it, so there isn't one correct answer, I guess. I would say it's rotating between 0 and 2 pi, probably, as you're rotating it around. So as we increment u, you can think of it like a for loop, like how we did in the code, or just mathematically, we're rotating around the cylinder. U is ranging from 0 to 2 pi. What should our value of S be as we go from 0 to 2 pi? Now, the way to think about that, 0 and 2 pi are relative, but if we think of this, starting in our x-axis going out in this direction here, where we start at x equals 0 and start at u equals 0, that should correspond to the very beginning of the wrapping paper. So we start at the beginning of the can, we paste that beginning of the wrapping paper in that dimension. By the time we get all the way around the can, that's 2 pi, we should be at the end of the texture corresponding to 1. So one such mapping would just be a linear mapping of the radians to our texture coordinates from 0 to 1. So it'd be just S over 2 pi. Excuse me, it'd be U over 2 pi would be equal to S. When U is 2 pi, we're done with the texture. That's S equals 1. When U equals 0, we're starting the texture. That's S equals 0. That would be one way to do it. And that's one way, if we have a mathematically defined object, we can just directly generate the texture coordinates in the same mechanism by which we're generating the positional coordinates for that same object. So they're related to each other. They're not exactly the same, right? X and Y are related to R cosine theta. Y is R sine theta, or R sine U. Our texture coordinates aren't in a three-dimensional space. Our texture coordinates are still just two-dimensional here between 0 and 1. So we'd have to do that mapping separately in our code that way. But it's kind of similar in terms of how we connect to the polar coordinates there. How about for t? What would t correspond to then? V would range 0 to some height value here. Just like we don't know the radius, but v would be either 0 to 1, and then z would be v times h for some height value, or v could be ranging 0 to height. Either one is fine. Let's assume v is going from 0 to 1, and that's how we range it, because it's not a sphere. If v if this was a sphere, v would also be rotating 0 to 2 pi, but it's not. It's just a cylinder, so v goes from 0 to 1, or negative 1 to 1, but whatever it is, it's just a scalar range we have for our v value here. What would t then correspond to? It would just be v. Yeah, in that case, it would just be, if v is going from 0 to 1, as I'm wrapping the paper, I want the entirety of this entire texture. So when we're at the bottom of the can, I want 0. When we're at the top of the can, I want 1. So t would just be equal to v. But that's not necessarily the only way to do it. There's other ways you can model the cylinder, and that would lead to different texture coordinates. But that's the type of scenario, and why you tend to see a lot of these examples as being boxes and cubes. And you can do a lot with parametric modeling of objects. So it's not really limited in that sense, but it's a lot easier to do that than to take just an arbitrary CAD exported geometry and object model and then apply texture coordinates, because you have to have an idea of what that texture should correspond to. Oftentimes, the modeling and the texturing are going, hand in hand, and that's a whole separate kind of software tool flow to generate texture coordinates while you're doing your modeling of some object you want to have in your scene. So when we're doing the rasterization task, and as we'll see from the vertex shader's perspective, the vertex shader is doing almost nothing with regards to texture mapping. You can apply textures at some stage during the vertex shading, but more conventionally, the texture mapping is happening in the fragment shading stage. So the vertex shader is generally just passing through texture coordinates. You are specifying them. You're specifying those S and T values. At the same time, you're specifying X, Y, Z values. So it's just yet another attribute for your vertices as they're being put into buffers and specified to pass through via these draw calls that we have here. So the vertex shader is just passing them through, and then it's the job of the rasterizer to interpolate it like it does the other parameters, the other attributes that we have here. So just like you have 3 points in a triangle, and you're currently interpolating X, Y, Z values, and right now you're interpolating RGB values as well. Well, if you're doing texture mapping, you're now going to be also interpolating those S, T values as well as we're doing it. There's some challenges associated with that I think are a little bit subtle, but as soon as you do your first texture mapping, you'll see this in practice. So we have a pixel space texture, right? Which we can map that in screen space. If it's from 2D to 2D, you can always stretch and shrink and do all sorts of things with an image, right? But now when we're mapping that 2D texture to that third dimension, and if we have any sort of perspective in our viewing of the scene, we have this same kind of issue, right? With a perspective view, as Z gets larger, those things should appear shorter, right? So we still keep our straight lines, but we don't necessarily keep any of our lines of parallelism or all of our lines of parallelism here. So we have potentially an issue, and you'll see this in practice if you're doing any kind of perspective view. You can interpolate the values here for our coordinates, but that doesn't correspond to a valid interpolation of our texture coordinates in the pixel space that we have here. It's easier to see when we're doing that interpolation via just some kind of checkerboard pattern here. So if this was our texture source, and I mentioned that on Tuesday, I'll say it one final time, your first code example should look something like this. So you can make a very simple texture, just a few lines in an array, right? And that's what your texture should be to start with. When we map that to this kind of triangle as part of our perspective view cube, and you can see that it's perspective view given kind of the foreshortening effect we see here with that back face versus that front face of the cube, what you presumably want when you take this texture and you map it to the side of the cube, I think it's fair to say presumably this is what one would want to see that texture mapped to the side of the cube. By default, if we're not careful, we wind up getting something that looks kind of like this, because we are doing the interpolation of our texture coordinates, but we're mapping it to geometry that's getting smaller as it's getting further away. That's getting this perspective applied to x and y as a function of z. When we were covering that topic, I never showed the matrices that wind up doing that scaling, but that's effectively what winds up happening. We change the w parameter, we wind up dividing everything by w, and consequently we wind up shrinking x and y as z gets further away. We've seen it now in practice, but that's what the matrix winds up looking like for our projection matrix that we have here. If we do that for x, y as a function of z, then to do this correctly, we also have to do that mapping for s and t as a function of z. So, okay, one workaround for you this semester is to just do only orthographic viewing of your textures, and then you don't have that issue. But we have to be careful, right? We have a straight line of regularly spaced points in our 3D space that leads to irregularly spaced points in device space. Things that are further away get smaller when we have a perspective view and we have a perspective transformation. If we want our texture to then map kind of equivalently to our 3D geometry with the texture view, and again, the assumption is that if you have this texture and you have this side of a cube, that this is what you would presumably want out of it. To fix that problem, you have to have a separate stage in your pipeline. Now, where we're doing that perspective division. I don't know if any teams are going to require that you do that. You can actually implement that in the vertex shader yourself. We talked about this briefly. It's not actually obvious to me. It's not clear to me with current driver infrastructure and the like. Where does this perspective division happen? Is there a custom piece of hardware? Is there some driver kind of microcode that gets added to every shader to apply that perspective division? Is there something else even more clever going on? We can certainly implement it in a shader. You take the .w parameter of your transformed vertex positions, you divide .x, y, and z by that w value to get the correct x, y, and z value. Long and short of it is however you choose to implement that division for anything perspectively correct, you then also have to do that for your texture coordinates. And that's just kind of a subtle issue that you have to take into account. Your normals are still pointing in the right direction, so you don't have to shorten any of the normals you have here. And oftentimes after we do the projection, we have to renormalize the normals so they're unit vectors anyway. But our texture coordinates, if we want our parts of our texture to appear to be far away, and you can kind of see it here, right? This black square is smaller than this particular black square as mapped to that triangle in our scene, to that side of the cube in our scene here. If we want to also make the square look smaller, we have to apply that foreshortening for those texture coordinates as well. So it's just an extra step. Vertex shader otherwise doesn't have to do anything at all with our texture coordinates, just kind of pass them along. But if you're applying a projection, the easiest way to check that would just be look at the value of w after you've applied the matrix vector multiplication of our incoming vertices, do a division after the fact to get the right result. In a sense, this is a nice problem to have. If you have this working and you see exactly this, you know exactly what's wrong and you can fix it one of multiple ways. So getting to that point is still a really good outcome here. So let's talk a little bit then next about the mechanics of doing that texture mapping. It's a lot of boilerplate code. The main challenge I would say associated with that is that there is a pretty large state space or parameter space associated with it. Specifically, there are a lot of different ways of specifying the texture data itself. There's also a whole ton of ways of specifying vertex data as well, and color data, all attribute data. But we have limited ourselves to one way of doing it, which is pretty common and supported. But there isn't just one common way of supporting texture data. It's really a function of what kind of format your textures are in the first place. They are image files to start with, or something generated in your code. And as many different image file storage formats there are that many different texture storage formats as well. So for your purposes, pick one that matches the data you have or the data you plan on having, and get that one to work, and that's probably sufficient. But you then specify the texture. You would say, here's my pointer, just like here's my pointer to my vertex data already in buffers. You're doing the same exact thing. Here's my texture data, here's my pointer to it. I'm generating a buffer in device memory, and I'm eventually copying that data over from my host buffer to my device buffer here. You then have to explicitly say And this is a little unique for us, although we're very likely to only have one texture mapping unit anyway. You specifically bind that texture to a texture unit. You're going to say, in my subsequent shader code I'm going to execute, there's going to be texture 0, texture 1, texture 2, and it's an OpenGL compatibility issue, how many of those one has to support. This texture is going to correspond to texture unit 0. This one's going to correspond to texture unit 1, etc. And you do the mapping that way. The next step is then would be in the application side of assigning those texture coordinates to those vertices. However you do that is up to you. Either they're provided for you with the model, you do some parametric modeling, or you're typing it all in by hand. However you have to do it, you choose to do it there. Again, if we're working on boxes and cubes, it's not so bad. But if you have a more complex object, it does get a little complicated there. And then you're specifying all the other, I would call them state parameters, of how that texture mapping should get applied. So I've used the term already. When we have pictures, we have pixels for picture elements. When we have textures, we have texture elements or texels here. You can call them pixels. They're not pixels, but they're very similar, right? They're discrete storage of a sample of some two-dimensional object we're interested in, and we specify them as an array in memory. This is one way of doing it where you have just RGB kind of byte array for your texture element. But there's many, many different ways we can specify an image. So as a team, it's not that big of a deal, but certainly when you start with your synthetic texture, your checkerboard pattern as you're doing texture mapping, decide as a team, here's what our texture elements are going to look like. Here's how many bytes per texel we're going to do, and here's maybe the sizes we're going to be able to support, and just limit it to something feasible. Your unit is going to grow in complexity as you decide to support other different types of texture formats. Otherwise, it's just any other buffer, any other pixel map in your code here. You then do bind texture to say, okay, I'm turning on texture mapping, and I'm going to bind this pointer in my host code to what is ultimately going to be a texture map in my GPU on my graphics application. You get to decide what your driver is doing. This would be the natural time when you call GL bind texture to do that copying of data over. But you could also do it when you're actually specifying the texture as well. I mean, in reality, in an application, you may be specifying a whole host of textures and selectively choosing which ones you're using at various different times, and that's a very natural thing to do, just like you would also be specifying a whole host of different objects in your scene, or potentially in your scene, and only drawing the ones you're interested in drawing at any given time. And so ideally you would copy the data over only as it's needed. In our case, just from a practical perspective and implementing things in the driver, you are probably going to support your own version of SGP_GL text image 2D with a limited set of parameters in which you raise an error if it's not a valid range for any of these input values you have here. You raise your own internal error when that's the case, and that's a reasonable time to copy things over as well. So specify first the type of texture. There's 1D, 2D, 3D. Someone asked a question about 3D textures, and my answer wasn't very satisfying, that it doesn't seem to be a very common usage scenario, that even when one does specify, and you look at examples that do three-dimensional textures, they're three-dimensional in the sense that the data source is three-dimensional, but they're oftentimes just slices of different two-dimensional textures just kind of glued together. So it's not mapping anything inherently three-dimensional beyond the geometry being three-dimensional. It's just a different data storage format than anything else. And that was the best example I could find that I posted on our Discord of why someone would ever use GL texture 3D. Likewise, 1D texture. I mean, textures can be used for any sort of data, not just kind of the final visible result. So there could be some value of having one-dimensional data sources we want to map to our scene. But I think, by and large, when you look at texture mapping examples, it's 2D texture on our 3D geometry. Level, by default, is 0, and I would assume 0 for all your purposes. We'll talk about mapping later today. Then, kind of similar to how we were doing the array buffer specification, right? You have the number of components per element. For this buffer here, which this is just one way of specifying it, you specify it yourself however you'd like. This is, in a sense, a three-dimensional array, but it's that inner dimension then is how many bytes per texel, then that's your your height and or this would be your width and your height here for how you're laying it out. So you would specify components, that would be the value of 3. Width and height would then be your 512 by 512. And we've talked about this enough. If you get it backwards, if your texture is actually kind of transposed here, it's an easy enough fix, right? Everything looks good except it's transposed. You'll be able to tell if that's happening. We'll talk about the border as well. And then specifically the format and type is saying what is the data, how should it be interpreted for those texels. There's many, many different combinations of GL text image 2D. One such example is the one we have here, RGB texels, each element being a single byte for the R, G, and B components here, and then the actual pointer to the array at the end of the day. Now, in theory, you can support all sorts of these different types of parameters, and I had to look up the total number of combinations. I have text parameter, I don't have the other one open here. All sorts of different combinations of format and type for the texels. And then you can choose to then do that conversion yourself in the driver, but it's how much driver code you want to write, I guess, is what you're determining at that point in terms of how you're going to store things in memory. Because I think it still makes sense from a hardware design perspective to say that no matter how many kind of combinations of data storage we're interested in here, potentially, it's going to get converted to some internally canonical representation so that your actual hardware is much more straightforward. That we know what our frame buffer is looking like, because even though we can specify different resolution and different color depth frame buffers, we don't. We have our specific frame buffer and color information. Likewise, you can specify a lot of different texels and texture mapping. We know ultimately the final end result in our screen is going to be in a certain format. You might as well convert your textures to that format as well. I think the result will look like what you expected it to. So that's specifying the texture coordinates. I don't have anything else to say other than, we have our X, Y, Z, and as we're specifying those attributes, we're also then specifying where in the texture space are we going to be sampling from as we're going to be applying that texture. Every time you specify a vertex, if you want to do lighting, you have to specify a normal. If you want to do texture mapping, you have to specify those texture coordinates as well. We have reserved one lane of our hardware attributes that we're passing down the pipeline here to specify those texture coordinates. Presumably, if you're going to be texture mapping everything, you no longer need to be specifying any color information whatsoever. You have probably, though, hard-coded your render output to expect your color output to be in lane 1. If lane 0 is positioned, lane 1 is our color. So you probably, although it may still work, you probably don't want to reuse that lane for texture coordinates. You probably just want to use the 3rd or 4th lane for your texture coordinates. But that's all fragment shader stuff then. You get to determine which attribute is specified, passed through in your vertex shader, applied in your fragment shader. As long as the output of your fragment shader, I think, still uses lane 1 for the resulting color of each fragment, it should all work. And render output doesn't know where the color came from. It's just applying or blending or checking depth for that particular fragment. Any questions? Are we going too fast here? Too slow? I can't tell. Okay, just the right speed. That's fine. We can talk about do some demos here. So here is what a lot of the OpenGL code tends to then look like for it. There's the internal kind of bookkeeping stuff that we do for all of our buffers. It's a little different in OpenGL for texture mapping, where there's a decent amount of complexity hidden in this call, where it is saying you have a certain number of fetch texture units, the separate piece of hardware that you're currently working on. You can have multiple textures that you can apply, and you're going to combine them together in various ways. You are saying that for the current texture we're working on, with this ID that we've just generated here, so that's the current active one, it's going to be on texture map unit 0 in your hardware. Assuming that you only have one, you have to still have this call for your OpenGL application to work. You probably don't need to do too much with that in your driver there. You may just be able to ignore that call. Similarly, for the binding of textures, again, your driver can do all that bookkeeping as well. If you're limiting yourself to one texture, just like we're generally limiting ourselves to one vertex buffer object. We support multiple, but we don't really explore multiple buffer objects. Then you're probably okay with whatever you do with the driver with regards to that. Then there's the specifying of the actual image. So my pointer, which isn't shown here, but my actual texels that are being loaded from a file or being generated here, this is how it should be interpreted in my texture map. That's probably where you're doing the copying of things over at that stage. You can't really do it beforehand, but for what it's worth, the order of these calls doesn't matter in practice. So you could see applications that do text image 2D first and then do bind texture. You can, it's your code. You can say our code works if we assume a certain order of these, and that's fine as well. And then separate from the actual specifying of the texture, there's all the kind of state space parameters you can still specify. How we're going to wrap in the S and the T dimension, how we're going to do some magnification, minification, how we're going to do filtering when our texture doesn't exactly map in that geometry to what we're mapping it to. It's a small texture being applied to a large object, or a large texture being mapped to a small object. That's our minification and magnification. How are we going to do that? And there's a few different states we can consider for how we want to implement that here. Let's look at what that looks like in practice. This is the same kind of application that we were talking about on Tuesday for lighting. So it hides a little bit of the fun that's going on here. Let me load it first, and then I'll know which one probably is the best one to look at to start with. That's wrapping, which that's not a terrible place to start. So wrapping is a relatively straightforward thing to wrap our heads around. No, no pun intended. So we'll look at this example here. So this scene is probably just a quad. Let's open it up again here. Just two triangles, okay? And as part of that scene, so we're specifying XY, 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 XY. There's our positional data. Doing the regular vertex attribute information here. When we look at what's happening here, it is a little different, right? Can we try to figure out what's happening with this call here? You normally need to have the shader and the software and the host code kind of side by side to really, understand what's happening here. It's a quad. We've been doing singular triangles, but we could have been doing quads throughout. So those are our 4xy positional attributes for the quad. They could have put a z in here, but it's two-dimensional. You don't need z then, right? So the default of 0 will work. These are then our texture coordinates, right? So we talked about it being between 0 and 1, but the example from Tuesday was also that you can do a value of larger than 1 for S and for T, and you get to then specify, and we're jumping around a little bit here when I say this, you can specify what should happen when the value is greater than 1 for S and for T here. Copy that attribute data over. So we push that attribute data out. And this is essentially how we've been doing it, except we've been doing it all semester for position and color, but otherwise it's the same. You're just saying, here is my relative attribute that's going to correspond to a location in my shader. 0 is position, give me those bytes. Location 1 is texture coordinates, give me those bytes associated with it. Turn those on. Now we have the actual texture mapping code that we have here. So generate a texture. That's like the internal OpenGL bookkeeping stuff to say I have this texture. Here it's not doing the call. That's the exact same one as on the slide, which is GL text image 2D, but it's a very similar type of call where we're specifying the type of texture. And here now we're saying each of these are just single byte RGBA values. So that is a different format that in that other example. But if you're doing something that's just very basic color, that should suffice. I wouldn't necessarily copy this example unless this is a format you want to be able to support, because at some point that conversion is going to have to happen. So this example I just kind of arbitrarily pulled up. But this example is a single byte for all the RGBA information. could just be what would be one way to do it? It could be 2, 3, 2, 1. This would be specified somewhere what RGBA corresponds to here. But it was RGB8, right? And that would be under text storage 2D. But same with text image 2D. 1 byte for the entire RGBA information with size 8 by 8, and so you're specifying that grid, and that's your texture you're applying for this example here. You could support that, but then somewhere, and I would say probably for you in your driver, you would then want to convert this back out to our 4-byte RGBA format so that you have something that's consistent with what the rest of the pipeline is expecting. Or you just convert it here in your host code and you use that 32-bit format. Then we're going to actually then specify that we have a texture of this size and it's corresponding to that pointer. Then we are specifying some of the texture parameters, and the one that's being used for this application that's of interest is what do we do when we have a value of S and T that is larger than 1. And again, I'm kind of skipping around a little bit when showing this, but I think we can figure this out, right? So for a parameter for our texture map, what do we do when we're wrapping the value of S? Meaning, in this sense, what do we do when S is larger than 1? And what is it doing when S is larger than 1? Clamping it to the edge, right? So what does that mean? Well, effectively it's saying when S is larger than 1, set it to be equal to 1. And then I do believe what then is happening here is there's going to be some code that's going to say where are wrap modes defined. Here they are. Here's the different modes they want to just play around with. And this is just an application that's trying to kind of show something dynamically here of change the different types. Clamp to the edge, clamp to the border where we have to specify what the border is going to be, or repeat, meaning S of 1.5, S of equal to 1.5 should be the same as S of 0.5, 2.5, so it's like a modulus kind of operation for the texture coordinate essentially. Or there's also mirrored repeat here. And as it's going, it's got its own little timer, and as it's drawing it, it's just changing that parameter every so often based on some unnecessarily complicated thing that's checking. Some incrementing tick, shifting it to the right by 11. So dividing it by 2048 and then checking if the value is 1, 1. So that would be, we should be able to figure this out. That would be like every 12,000 ticks, right? So when it's 1, 1, 15,000, 16,000 ticks. Every 16,000 ticks, change the mode that we have here. So with that in mind, let's see if we can see it kind of side by side what's happening with this application. And let me start it up again here and kind of show those modes side by side. Clamp to edge, clamp to border, repeat, and mirrored repeat. I guess we could change the code. We got in trouble last time we did this. To do it slower. So every time I change that value from 11 to 12, it should double the amount of time it'll take to switch, I think, right? Because it's dividing by, equivalent power of 2. So it should take 4 times as long to do that here. So humor me. Oh, because this is using CMake. There we go. And this one I don't care if I break. All right, so at least should hold up for a little bit longer than it did before. It doesn't look good stretched. Okay, start up again. So let's take a look at, let's try to figure out what's happening here, right? By default, we start this application, and maybe this is obvious, and I'm cool with that as well. We have a texture map that is, in essence, a checkerboard pattern. But unlike specifying an image, we're going to be applying some mapping here. We don't have to specify, a block of 64 by 64 texels for black, and then a block of 64 by 64 for white. We can just specify, assuming we're doing our sampling correctly, black, then white, then black, then white. We're specifying a texel by texel checkerboard here. It's an 8 by 8 grid where each element is just alternating between, I guess, white is first and then black for each element that we have here. And then while we are specifying our geometry, which is just a simple quad at this location, we're also specifying our texture coordinates. And let's change that, since we've shown our ability to compile things properly on this dated platform. Let's change it to 0 and 1 again. So if we were to look at what's happening here, lower left-hand corner of our quad, lower left-hand corner of our texel, lower right-hand corner, and et cetera, right? So it's mapping lower left to lower left, and it's mapping basically dimension of our texture map to dimension of our quad. But this is in our 3D space, right? Or it looks 2D, but this is in our 3D space, after which we are applying some transformations to it. Even if there's kind of the unit matrix or the pass-through matrix transformation here, this is going to correspond, given the resolution of our viewport, to an object that's in our screen space. After rasterization, we're then going to have a value of range, value for S and T ranging between 0 and 1. That ranging is also going to be potentially in our screen space, in the sense that as we have our rasterization, we're going to generate a certain number of fragments, right? Corresponding to our X going from negative 0.75 to 0.75. We are going to generate an equivalent number of texels then as well, because the rasterization is just treating the texture coordinates like any other parameter. So as we have that many fragments we're generating, that fragment is going to have an X and Y value. It's also going to then have the same number of S and T values. Presumably, as we go from negative 0.75 to 0.75, as we range over 1.5 in our floating point space for X, we're going to range over 1.0 in our floating point space for our texture map as well. So now, although we changed it so it's not actually doing any of the texture wrapping kind of modes here, this isn't actually the application I want to run. We get something that looks like this. We only specified a single texel for black, then white, then black, then white. Lower left-hand corner here is where we started. It's the very first texel we're specifying here. So there's a little bit else that's going to still have to happen here, where we're going to do our texture mapping, and we'll look at what that looks like in the shader as well. And when we do our texture mapping, there has to be some kind of filtering and averaging that's potentially going on here, right? We are specifying an S and a T value in our fragment shader, and we have to sample from that texture map. That's being specified here. We'll talk about what that means in practice, but we have to be able to get from just having a single texel specified in our actual memory for our texture to being able to fill out this entire grid effectively. For this, because we're really magnifying it and it's a checkerboard, just truncating the value is probably sufficient, right? You'll get a value of S equals 0, T equals 0 right here. And then as you move here, well, what will you wind up getting? You'll still get like, well, let's say this is, I don't know the resolution here. Let's say this is 50 pixels along in our screen space. You'll get a value of 50 over 1024 for S and for T. Well, rounding will probably still work. That'll still work out to be texel 0, 0 here. Only when you get far enough along that you're 1/8 of the screen along, because that's how big our texture map is here, you'll get a value that corresponds to the next value of 1/8, I guess in this case, 1/8, 1/8 for the texels that we have here. So it's a sampling of this small array in this case, and it's expanding it to our larger quad that we've extended in our screen space here. Now if we go back to, I think that's sufficient. Now as we go back to this version that's now changing the modes, and it was still changing it too fast for my liking. Now all this application is doing is we have these larger texture coordinates, and we're specifying, well, what do we do when S is larger than 1, when T is larger than 1? By default, and it should take us a little bit of time for it to swap, it's going clamp to edge. take whatever happened to be at the edge of that texture map. Let's restart it again. Whatever happened to be at the edge of that texture map, and continue it on here. So that's not exactly what's happening here. For this example, as S is getting larger, because it is happening. It's hard to see though, is all, because it's just black and white here. That is what's happening here. You can't. Kind of hard to see. The grid doesn't end right. Oh, my mouse is really small. I know. The grid ends one little. There needs to be like a border or something. So it is clamping to the edges. It's kind of an optical illusion because it's only 7 by 7 inside here. The 8 by 8 is the ones that are outside here. Then we go from clamp to edge to clamp to border, where you specify what you want the border of this texture to be. That might be 0 by default, or maybe in the code it's specified somewhere where the border was going to be. Then we go from clamp to border to repeat, which is kind of, you can think of it as like a floating point modulo operation, which is effectively treat 2.0 the same as, or 2.5 the same as 1.5, the same as 0.5 for those values, and that gives you kind of a hypnotizing, really detailed one. And then the mirrored repeat is very similar, but it's effectively 1 minus S and 1 minus T, which leads to kind of sort of trippy looking results here. And if you stare at that long enough, it looks like something's moving, but it's actually quite static. You'll have to take my word for it. We didn't look at the actual shaders for this example. They were certainly here. Here they are. I scrolled through it too quickly here. In this case, the vertex shader is doing basically nothing. In this case, we specified an X, Y, and I don't think it matters, but it's specifying a Z value. But that's all it's doing here. So a hard-coded Z value for the X, Y that are being passed as our input here. And for our texture coordinates, it's doing nothing. We still require that step. Our rasterizer is not aware of anything that's not passed as the output of our vertex shader here. So we have our input texture coordinates, our S and our T. It doesn't really matter. Just pass them as our output, a pass-through texture coordinate vertex shader, essentially. Now for our fragment shader here, and we'll talk a little bit about what this means, is the only thing we need to know for these is what our texture coordinate is from as the output of our rasterizer, and we do need to specify our color. What should the resulting color be? And this is using, this is version 3.3. It's not so different. We have this sampler 2D, which is a new kind of uniform specifically for specifying the type of texture mapping we want to do. For now, you can kind of assume that as boilerplate, but now we're saying our color is going to be the result of performing that texture mapping. So it doesn't really show what's happening there, right? It's effectively emitting, I would think that this itself would be a single instruction because it would be loading a constant. So you have to specify that text uniform. You can think of it as a pointer to a texture unit because it is kind of like that. It's saying, here is the texture unit we are going to be specifying. And then effectively one instruction that takes as input that vector of texture coordinates and applies it to that texture unit that we're binding to this operation and doing that lookup and returning that value here. So in a sense, it's a single instruction, but there's just a lot of hidden state associated with that, and that's why the complexity can potentially grow. Think about it though. You're taking an S and a T value of 0.5 and 0.5, for instance. You need to know, in this hardware corresponding to this texture unit, what does 0.5 and 0.5 correspond to? So you need to know effectively everything that's been specified up to that point. So another way to think about that is like your software accessible registers for your fragment shader, you're going to need a lot more of them, or a region of memory that it can read from. But either way, you're going to need a lot of parameters, right? Because it's going to need to know what is the format of my texture. At the very least, it's going to need to know the size of the texture coordinate, of the texture map. If it's 8 by 8, then 0.5 corresponds to like 4, right? If it's 8,000 by 8,000, it corresponds to 400. So your hardware is going to have to do that lookup, that kind of translation of S and T into either first 2D textile coordinates in an address space, and then finally converting it to a final address, which we also need to specify. Somewhere the driver then also needs to say what was a pointer on our host side becomes a pointer on our device side. We call it a base address, right? But it's just a pointer as well. That needs to be part of what your texture mapping unit needs to be aware of as well. So once you have that, it's okay, I think. And if you were able to get depth working, there's a lot of similarity there, which is take base address, take this new computed address as a function of our x and y, but now it's of our s and t, and do the lookup at that point. The difference is that kind of simplified things is we made our frame buffer of a fixed resolution. So that x and y to frame buffer lookup for color buffer and for depth buffer is kind of fixed. Maybe you didn't set it up that way, but it can be fixed. It's 1920 by 1080. If we wanted to change the resolution, all of your render output code is probably not working, would be my guess. For this though, unless you are deciding as a design decision on your own, I only want 512 by 512, I'm not going to support anything else, then it's not a constant multiplier, then it's a register multiplier where we're saying, I need to know the width dimensions, I need to know the height dimensions. And then in addition to that lookup, some of these will be pre-lookup and some of these will be post-lookup. But in addition to just that basic lookup, you have to determine, do I need to support any of this? And that's also up to you in some sense. But for example, if my S value is greater than 1 or my T value is greater than 1, what should that lookup correspond to? Again, the assembly instruction call doesn't see any of that complexity, right? So it's kind of misleading in the sense, oh, just calling texture fetch and I'm done. But now there's a lot of kind of hidden state associated with that. Before I can calculate the address, I need to know what should I do in case the address is actually, or the parameters, S and T, the attributes, are no longer in the range 0 to 1. I can choose not to do a texture lookup. I can just clamp it to 1, which is what is happening by default here. I can do some wrapping operation. So whatever your application needs, support something I think is necessary for that. And then, we haven't talked about the filtering that happens, but some sort of filtering has to then happen. The example it's doing here is nearest filtering as a default. There's other applications here that are doing different filtering examples, because what will ultimately happen is you'll have your S and your T value, and it's a floating point value, right? Or it's in our fixed point format. But it's got to ultimately correspond to an address in memory. And just like the issue with aliasing, where, well, things kind of fall in between a pixel address, it's going to happen, significantly more in this case, where things are going to fall in between a textual address. It's not this one, it's not that one, it's kind of half of each. And so the challenge then becomes, when you're doing your texture fetching, are you okay with just rounding, which is what this is doing? Wasn't actually Texel 1001 or 1002, it was actually 1001.5 or 1001.6. I'm just going to grab the closest one. You can also truncate as well. I'm just going to grab 1001, I'm going to drop all the fractional component there. That will lead to different visual effects depending on how big your geometry is versus how big your texture map is going to be. This is kind of a fundamental challenge in doing texture mapping properly, and we talked about that. I want to talk about that a little bit here. So let me skim over before I get to that. You can do lighting in addition to texture mapping. There's nothing preventing you doing both. You can then specify that you have the entire lighting module. You can either replace it with the texture, you can kind of add it on top of the texture, or you can do some kind of modulation of the texture with what the lighting model would say. So there's no reason that that's not something you could implement, at least in the shader code itself. If you already have the Phong model, as we've talked about earlier this week, last week, if you already have that working, you can add texture mapping on top of that and get reasonably good looking results here, where it's both mapped with a texture, but as we see here, it looks kind of three-dimensional, but maybe not as three-dimensional as we'd like. Now when you add that lighting on top of the texture, you get that nice looking happy fun ball again. I'm going to pass over the wrapping, but there's the different possibilities for the wrapping. We showed the demo here. So the real challenge then is what to do with regards to magnification, and I think I wouldn't be doing my job if I didn't bring this up. We made sure we understand it. So what happens when you're getting very close to the textured surface so that you can actually see, and there's a discrete step between each individual texel? That's referred to as magnification. And the type of solutions we do are very similar to that for anti-aliasing. One such behavior is just to take a neighborhood sampling. So there's point sampling, where you just take the closest one. If you get that working, you're still in pretty good shape. There's then various types of other sampling mechanisms. One example is bilinear sampling. Give me the neighborhood around the texel that I've specified here and average those together. That's for the magnification problem. That's very similar to what one would already have to implement for anti-aliasing. I'm not exactly falling on an exact texel boundary, and if your geometry is a different size in screen space than your texture map, that's always going to happen. If it's not magnification, you will have the issue with minification as well, and it's just an averaging approach. It's the exact opposite issue which we don't normally have when doing traditional rendering with our anti-aliasing. So the idea here is that when we have a texture and we're viewing it from very far away, it's still a sampling issue, but it's not the same as the texture being blown up too close where we have like discrete issues in kind of the jagged view of it. Now our texture map is of a certain size and that's fixed, and we have an object is getting progressively further and further away. This would generally not look good if we applied the same approach. If we just tried to sample a neighborhood, very small changes in our geometry would wind up leading to very large changes in the resulting texture that gets mapped. And I wish I had a good demo for it, but it leads to kind of a shimmering effect where as your object is moving very slightly away, it's completely changing what texture and what parts of the texture map are being applied to it. The most popular approaches for dealing with this level of detail type of optimization in which you have a certain fixed texture map, but you have geometry that is potentially either going to be magnified or minified because it's too close or too far away. The general approach is referred to as MIP mapping. Has anyone heard that term before? Okay, a couple of you at least heard of it, but not really familiar with it. Okay, well, good. We learn all that we need to learn from Minecraft. Again, it's rarely going to be a one-to-one thing. Magnification is one such approach when it's really far away, and then that address corresponds not to just one texel, but a whole bunch of texels. In theory, you can still do an averaging, but the end result doesn't look very good. The common approach still used today, referred to as MIP mapping, and there's all sorts of either automated or kind of manual efforts to provide different scalings of the textures that are provided here. The idea is that instead of just storing the texture itself, just the texture you intend, you actually stored multiple, either manually offline or allow some of the software infrastructure to generate for you to kind of pre-compute a texture map of a certain size and texture maps of subsequently separate sizes. Generally, for the minification problem, you're not worrying about upscaling your textures, but you're worrying about an offline downscaling of your textures. So you have the 512 by 512 texture, which can be good depending on what geometry is being mapped to, but then you also then generate, and OpenGL provides functions for you to do this generation, the 256 by 256 and a 128 by 128 and a 64 by 64, all the way down to like a 1 by 1. What should that single texel be if it's scaled all the way down? And I mean, ultimately, you're losing information in each step. You're not like solving the problem of something that is of certain resolution getting kind of scaled back down, but it eliminates that issue of that sampling issue being kind of arbitrary. So yes, you have a complicated texture and you sample it all the way down to 1 by 1 and it becomes gray or brown or something like that as you average everything together. But at least it's fixed. And so when you're doing that mapping at that smaller texture map, you're not getting that shimmering kind of effect. You're getting the same texel being mapped no matter what the size of your geometry is relative to that 1 by 1 texture map size. So the idea is, instead of worrying about the size of your texture map and how it's going to map, when doing the texture fetch operation, you map and store multiple copies of that same texture map. From a memory storage perspective, downscaling is okay, right? There's overhead, but it's not as bad as you think, right? Because it scales quadratically, right? And we're shrinking the dimensions. We're downscaling, not upscaling here. So you store your 512 by 512. In addition, you store 256 by 256 all the way down to 1 by 1. And mathematically, that adds 1/3 extra memory per texture. So you're not actually storing or wasting a ton of extra memory in doing so. So then what winds up happening is you have a storage that looks ultimately, although it doesn't have to be stored in memory necessarily in this fashion, something like this, where you have a certain amount of storage for the original texture map that's RGB, and then you downsample by half, downsample by half, downsample by half. The only then trick from the texture fetch perspective is then just determining which texture map or which texture submap of all the texture maps you've now generated for that single texture one should actually be doing. And again, it is just effectively averaging or sampling, although there's different approaches that can be taken to downsample from this size down to this size, down to this size, down to this size. But it's a fixed pre-computed downsampling. So given the size of a geometry, it's going to apply texture mapping still and do either bicubic or other bilinear sampling that's going to happen here, but it's not going to take it from the large texture map if in fact the geometry is more appropriate to be sampled from this size texture map. And I don't think I have a great example of, well, we can look at the code here of which one, where it's actually doing that specification of which value that we have here. So I'm less interested in the trilinear filtering here, which is, again, just averaging of neighboring pixels. Let's look at the example for MIP mapping here. That's the filters. So this example, MIP mapping, it's doing some rotations and stuff. From the fragment shader's perspective, has no real knowledge of this, right? So it's happening in the fragment shader, but the actual shader code is still very straightforward. Here's your sampler, apply a texture fetch to it. We have a little bit more complicated geometry in this example, but not terribly more complicated. And as we specify, we have a 64 by 64 geometry here, and we're specifying, give me the nearest MIP map in a linear filtering approach here. Let's run this application, which is 606 MIP map. We will not run that one. Let's look at MIP map filters. Okay, not the example I showed here. This will take a little bit of time to kind of walk through what's happening here. So it's again just a set of checkerboard patterns. I have it open. This one's gonna be a little tricky though. It's cool, but if I can't explain it, it's not really serving its purpose. Where are we doing the textures here? It is a more complicated checkerboard pattern here. So this one's gonna be a kind of a pain to walk through how that's actually happening here. What we could then change is, this is how it's doing the magnification. By default, it's just doing nearest. And this example is changing over time how that filtering is happening via slide. So we should see this filtering change. I couldn't really read exactly how frequently how that filtering should change, and the results might be a little bit subtle. Let's leave things here for today. I'll continue to stare at that and let you know if I see any, because it's changing filtering for a arbitrary checkerboard pattern. It might be extremely subtle to see any actual differences here. Let's leave things here for today. Again, for your texture mapping that two of you are doing for your projects, start very simple. Recognize that the actual shader code is very straightforward, right? You're basically supporting one uniform type, just kind of like a hardware pointer to which texture map, but you only probably gonna have one texture map per application, probably, and then an actual texture fetch. But then there's all the other kind of driver state that you either have to assume kind of same defaults, or you have to decide as a group, what things are we gonna be able to support? What's necessary for us? What can we kind of ignore for our purposes? And get checkerboard working first, and then worry about the rest after you get your checkerboard working. Let's leave things here for today. I'm going to stare at this until something good comes of it. So otherwise, I'll see you guys next week.